So thank you very much, Professor Longo, for having accepted our invitation for our PROTEUS seminar series. Today, Professor Longo will talk about modular time and quantum information. So I leave the stage to you. Thank you very much, Professor Longo.
Thank you. Many thanks for this invitation that was truly stimulating with me, because I think it is important that people in different areas communicate, and so I took this as an experiment, but my experience is that when people working in different areas communicate, that something good always come out. So what of course, it's very difficult to in a talk to give an idea of a subject and what I am doing and so on. So I will start with the origin, giving some idea, mentioning some fundamental fact, and tell you what I'm doing at the moment. But of course, there are many missing results and subjects that I should mention, but of course I have no time. So it's the first thing I want to do is the way of thinking in different subjects. So this applies not only in the relationship between mathematics and physics, but also, for example, different way of thinking internal of mathematics. And I give you a test just to start. So we have a closed curve, this blue curve, and then there is a point in the middle, in somewhere internal. And then the question is, it is possible to draw a straight line so that the straight line will intersect this curve at 2 points at equal distance. So if you ask people, even mathematician or a mathematician and a physicist, typically you get 2 answers. One answer is, okay, I draw some line, and then I try to rotate, to try it, and then to find a critical point, a minimum. So it's solution. It's a dynamical process. There is another way to answer, which is in a sense just thinking. It's a meditation, if you want. You take this point and you construct the curve which is symmetric with respect to this point. So for every point you draw the point at just opposite to this point. Then these two lines, these two curves, the blue and the opposite, the symmetric curve will intersect, at least in 2 points, and these 2 points are the solution. So this is just thinking, and sometimes people say this is a Oriental way of thinking. The dynamical one is the Eastern. In any case, I don't know which one came to you first in mind, but it's quite important that 2 ways of thinking collaborate. And this applies to the cycle mathematics and physics. Of course, mathematics at the very beginning comes from physics, because we are people that we look, for example, we try to understand what is to count or to make some measure, not this physics, and then we want to make a square triangle, for example, and then comes mathematics, which takes this idea as an abstraction, and then mathematics proceed just once mathematics as an idea, then just abstractly construct other structure. And for some miracle, this idea goes back to physics, and maybe many years, even centuries later, they are successful. At least this was the situation so far. So physics consolidate the ideas by experiment, make some theory, then goes to mathematics, and mathematics proceed just by formalism, which is an art to mathematics, and then comes back. This was a very, there is a very famous paper by Eugene Wigner, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. I think it is not true that the paper is famous. The title of the paper is famous. Few people read the paper, but the title is already condensate what the idea. I remember when Israel Gelfand came to Rome 20 years ago, and Gelfand was one of the most important mathematicians of the 20th century, and he said that mathematics is an art, like it's a mixture of art and formulas, like music. He also added, but if I will be born again, I will do music, not mathematician, not mathematics. The reason is that many people understand music, it's easy, but it's not easy to communicate mathematics. This is truly the point about mathematics. It's difficult to communicate. Now, let's go to time. Time, what is time? This is, of course, it is a big philosophical issue. But we may say, we start to say something, that if you look at the classical space, classical mean before quantum, and we can imagine, just imagine, that a space which is completely static, no movement at all. In this situation, time has no meaning, because if you have only one configuration, the time has no meaning. But then, if you have several configurations, then you order. So something comes first and something comes later, and then times appear just as an ordering of different configurations. But when we go to quantum spacetime, there is this phenomenon of quantum fluctuation. There is no static quantum spacetime, just because there is always creation and annihilation of particles, for extremely short time, but yet
is a leading customer, Swiss Telecom.
I cannot hear well. Can you repeat?
No, I think it was just someone that didn't switch on the microphone when entering the room, so you can continue.
Okay. So in a quantum field theory, in a quantum space, there is a spontaneous creation and annihilation of particles, so there is no static spacetime. So if we look at the space from the quantum point of view, there is no static quantum space, so there must be a time. So time is in a sense intrinsic in quantum theory. Now, what is the difference between classical and quantum? The essential, the fundamental difference. It is non-commutativity. Classical spacetime is commutative, and quantum is non-commutative. I will tell you something in a moment about that, but this is the crucial difference. So we may say that non-commutativity generates time. So let's start again with the arrow of time. And if you look at classically the arrow of time is understood, is defined through thermodynamics. Newtonian mechanics is reversible, but thermodynamics is not. So heat tends to go from something warmer to something colder, and not the other way. So there is only one arrow time. In quantum mechanics, there is another possible quantum arrow time, because when we make a measurement, we go from a mixed state to a pure state, and also this process is irreversible. So there are two ways to fix the arrow time, and a known question is that is there a general frame to encompass both, or in another, or even more ambitious, can one derive one arrow time from the other? And of course, if we try to answer the question, we should keep in mind that the time is a relative concept, as we have learned from relativity theory of Albert Einstein. So the origin of quantum mechanics, of course, quantum theory started, as you know, by Planck, but quantum mechanics were developed in two ways, independently, by Schrödinger and by Heisenberg. And Schrödinger was based, the description was based on this Schrödinger equation, so differential equation if you want. But Heisenberg description is based on the fundamental relation, commutativity relation, commutation relation between momentum and position, and which says that they do not commute. No? It's a multiple of the identity. And for Neumann, so this was the situation for 1 year, but then for Neumann, phenomenon came and proved the theorem that the two pictures are equivalent. One can pass from one to the other. So these two pictures are equivalent, but in the Heisenberg picture, so more clearly the non-commutativity comes out, which is the fundamental difference. Now, there was the quantum mechanics when quantum mechanics came, there was a critical moment in the communication between mathematics and physics. Why? Because quantum mechanics require this new mathematics, which is non-commutative. And mathematicians did not have this framework, so physicists tried to set up this new mathematics in heuristic terms. And physicists were not interested in mathematics. Well, of course, with the due exception, but generally speaking, were not interested in what mathematicians were doing. And mathematicians were not interested in what physicists were doing, because it was certainly not a truly mathematical world. It was heuristic. And this was in particular in the situation in Italy was peculiar, because a lot of young people died before the war. So there were not enough people, good people, to support both mathematics and physics. So the mathematics had a very high tradition in geometry by Ricci, Levi-Civita, and also functional analysis like Volterra. But young people went to the Fermi school because that's what was attracting the good people. Now the situation is quite different, and personally, I have the fashion to meet my advisor Sergio Doplica, that introduced in my laurea in mathematics, coming from physics, and he introduced me to the operator algebra subject. So operator algebras. What is operator algebras? Operator algebra is a subject that von Neumann developed, and at the beginning by alone, but soon later he wrote a monumental work in collaboration with Murray, and this is the list of this opera, developed with he had in mind to set up this new mathematics that was necessary to describe quantum mechanics. And it is quite interesting to see that this monumental work was not cited almost for 10 years, with one or two exceptions, which was not truly important. So it was necessary to wait to absorb and to understand this great work. So what are the basics of operator algebras? So we have a Hilbert space. As you know, Hilbert space is maybe infinite dimensional, so it is the natural generalization of the Euclidean space. And then one consider the linear transformation, bounded, which means continuum, on this Hilbert space. And these linear operators or linear transformation, of course, have a linear structure. You can add, you can multiply them. It is a star operation, the adjoint, like for matrices. You can conjugate, you take the adjoint on matrices. But there are more structures. There is an order, so you can say an operator is positive if it is of the form B star B, like a number, a complex number is positive if it is of the form B star B for some complex number. Then there is a metric structure, there is a norm, which is just the best bound of the constants that dominate A star A. And then there is this C star norm of the property, that the norm of A square is the norm of A star A. And if we have an algebra with this property, this is called a C star algebra. Now, Gelf and Neumann made a fundamental result on commutative C star algebras. So what they proved, that every C star algebra is a C star algebra, is isomorphic, naturally isomorphic, to the algebra of continuous function on some compact space. So if you have a compact space, we can consider the algebra of continuous function, which is, and if we have a commutative C star algebra, we can consider the characters of one-dimensional representation, and then this operation are in duality. So it follows from Gelf and Neumann theorem that every C star algebra is isomorphic to a closed star algebra of B of H. So B of H, the algebra of all bounded operators, contains all C star algebra. And so we have non-commutative geometry by Korn, then also refine this. So we want to generalize the fact that X is a manifold, rather than just a topological space, and it is the notion of spectral triple that I will not explain here. Rather, I will go to the concept of von Neumann algebra. Von Neumann algebra is a C star algebra, so it's a closed, non-closed subalgebra of B of H, but which is algebraically closed in the following sense. We consider all operators that commutes with all operators in M, and then we take twice this operation, And if we get the same algebra, so M is the set of operators that commute with all operators that commute with M. Then in this case, it is a von Neumann algebra. And if you look at commutative von Neumann algebra, then this is isomorphic to L infinity, measure space. So von Neumann algebra is a non-commutative measure theory. Like, why these are the good for the description of physics, because observer in quantum mechanics will be self-adjoint element of a von Neumann algebra, and states are normalized positive linear function of field. So we have this linear function, which is positive and normalized, and the expectation value of the observer x in the state phi is phi of x. This is the formalism. So the general structure is the following. In the commutative case, we can have, for example, a manifold. So the algebra is the algebra of a smooth C infinity function on the manifold. And the quantum analog is a star algebra, which can be non-commutative. Or we can just more generally take X as a commutative space. Commutative X is a topological compact space, and then take the algebra of continuous function. This is a C-star algebra that in the quantum case can be non-commutative. In the concerning von Neumann algebra, the classical von Neumann algebra are measurable, bounded Borel function, let's say L infinity function more precisely, over some measure space, and von Neumann algebra is just what I told. So this is a scheme of the mathematics that comes. I don't think I will dwell on that, but today's, at least my and the people that work in the operator algebras and want to look at quantum field theory, they look at this scheme. So from classical variables, let's say one can go first classically with infinite dimensional manifolds, but non-commutative they go to subfactor, modular, endomorphic, whatever it means, or one can take the other part from classical value, one can go to quantum geometry of finitely many degrees of freedom, and then quantize. And now this was the general picture, and now I wanted to go to some concrete problem that I have been working on very recently. I am still working on that. And quantum information, but quantum information, I am interested in quantum information of a system with infinitely many degrees of freedom, because I have always in mind quantum field theory. Quantum information, as you know, it's a growing and hot subject. There are many interesting results, but most of them concern finite dimensional systems, which is motivated by many things, for example, quantum computer, etc. But when we go to large system that we can consider just infinite, then there is something new that we have to work out, and I'm working this direction. So the problem that I want to discuss now is the following. We have Alice and Bob. Alice sends a signal to Bob through a wave, for example, like electromagnetic waves, like what I'm doing now. I'm transmitting you some information through waves. But Bob measuring as a laboratory and measure and get the signal, but he gets the signal only for a limited time and only on a limited space. So Bob has access to the signal only for a bounded space-time region. So the question is, how much information can Bob get? So in other words, can we define the local information? Or if you go into too small at a point, the information density in a wave. This is a completely new problem, and that I will formalize now. So what is the equation, the wave equation, possibly with the mass? It's called the Klein-Gordon equation. It is following. So there is the second derivative with respect to time minus the sum of the Laplacian, the second derivative with respect to the other directions. And then this equation, when m is equal 0, it's called the wave equation. Otherwise, it's called the Klein-Gordon equation. It is an important equation because it appears in quantum field theory. In particular, it appears in classical physics, but also in quantum field theory. And if you want, the famous Dirac equation is in quotation mark the square root of the Klein-Gordon equation. So this described from the quantum point of view, boson and Dirac equation describe fermions. And the solution of the Klein-Gordon equation can be given by the Cauchy data. So the value of the wave at time 0 and the value of the time derivative of the wave at time 0. If we know this value, then there is a unique solution. And in classical field theory, there is a notion of stress energy tensor, T mu ni, that gives the energy momentum density at any time. But what is the information of the entropy density? So what is the information, the entropy carried by the wave in a given region or a given point at any time? And I will see that will give you a classical answer like this classical question, but by quantum field theory. And in fact, this will give also, this answer will have a meaning in quantum field theory. But since the mathematics is the same, you can read either classically or quantum. And to do that, I have to state something that I understand is difficult to understand right away, but it was truly a fundamental result in operator algebras, and in my opinion, one of the most important results in mathematics, generally speaking, which is the Tomita-Takesaki theory. What does theory, the main theorem of this theory, say? Then suppose we have this phenomenon algebra. So it's phenomenon algebra consists of operator on some Hilbert space. So we can take a vector, unit vector on the Hilbert space, and then the expectation value will be a state. So we can embed the phenomenon algebra as a linear subspace of Hilbert space, just evaluating. So you take an operator in M and X, and then I go to apply to X omega, I get a vector. Once we do, and if the vector, if this application is a one-to-one, so which is a rather general factor, then I can read the star operation on the Hilbert space. That will be an operator, that's defined. I can write what's called the polar decomposition. In any case, I get operator, and the miracle is that this operator delta, the modular operator, exponentiate, and this was the logarithm delta exponentiate, and gives automorphism the algebra. When J set up an anti-isomorphism with the algebra and the commutant. So algebra and commutant play the same role. They are anti-isomorphic. One is the mirror of the other. But any state, any with the very general conditions, cyclic and separating, we say, then gives rise to an evolution. So for Neumann algebra, if you look at classical L infinity, there's no evolution. Of course, you can put by ends, but here there is an intrinsic evolution. Just the fact that you give a state, then the system evolves by itself. There is an intrinsic. This is the modular evolution, and this parameter, I will call it the modular time. And Tomita proposed this in 1977 at the Baton Rouge conference. This was the first conference on operator algebras. And Tomita distributed this preprint, but by an historical accident in the same conference, Rudolf Hager proposed what should be the characterization of thermal equilibrium states, KMS states, and Takesaki participated this, it's very young, at this Baton Rouge conference, and he fixed, because the Tomita preprint was some errors, he fixed, he completed Tomita theory and showed the equivalence with that the modular group is characterized by KMS condition. So among the many properties of important properties of the modular group, let me single out the following three. The modular group is a purely non-commutative object. You don't see the modular group if you remain in the classical framework. The modular group is a thermal equilibrium evolution, in the sense if we are in the matrix algebra, no? in a small infinite dimensional system, then a state is given by density, the density matrix, and the evolution is given by exponentiated the density, the logarithm of the density matrix. And these are the so-called Gibbs thermal equilibrium states, I will tell you in a moment. And then there is a Conner-Radon-Nikodym theorem that if we choose different states, of course we have different evolution, but these evolutions are different only up to inner automorphism. In the abelian case, there is no inner automorphism because, but in the non-commutative case, every phenomenology has a lot of inner automorphism, and this evolution does not depend on the state up to inner automorphism. It's a completely intrinsic quantity. So what the scheme is the following. Quantum physics gives this KMS, which is thermal equilibrium condition with positive temperature, but it's equivalent to say that the flow is a modular time. So we have a time, the modular time R of time, and this gives a positive entropy, and this is related to the thermodynamical R. So in this scheme, if you want, both there are two R of time, they are put together. There is the thermodynamical R of time, and there is the modular time, and the quantum, the Gibbs R of times, and they are put together by the modular time of time. So in a sense, modular time unify the two R of time, the classical one and the quantum R of time. This is just to remind you what was for finite quantum system the equilibrium time. When you have an evolution given by just adjoint to a one parameter group of units in a matrix, so exponentiated self-adjoint matrices, this you normalize this the Gibbs, you get the Gibbs states with density matrix E2 minus beta h. Beta is the inverse temporal. You normalize, and then these are the KMS states in the finite dimensional system. So KMS states to be generalized Gibbs states. and this is the equation of KMA states that I will not perhaps dwell on this, but the KMA states, KMA states say that if you take a state and you have an evolution and a state, then of course, if the evolution is trivial, this just means that we have a trace, x, y, and yx are the same, commute under the state. But in general, KMA states that we have to make an analytic continuation with the evolution to pass from x, y, and yx. So the commutativity here as this manifestation. The thermal state, for infinite at infinite volume, for infinite system, are described by this KMS condition. This is on the left you see the original preprint by Tomita that was never published because in fact the people didn't believe in it for certain data. As I said, they contain some errors. And then on the right you see the lecture notes by Takesaki on Tomita's theory. These are the historical papers. Now the generator of the modular group is called the modular Hamiltonian. Of course, we can embed the phenomenology in the space by two vectors, not by one, and then we get the relative modular operator. So log is still the modular Hamiltonian. And a modular Hamiltonian is a quite important object, and nowadays it's quite a hot topic in theoretical physics. So if you go to archive and digit modular Hamiltonian, you will find a lot of papers because now the reason is that mainly because of entropy, as I will explain, but there are also other reasons. Now, let me say something of the general framework of quantum field theory. Quantum field theory is a huge subject. So if you ask two different experts what is quantum field theory, I think you get two different answers. There is a part of quantum field theory that deals with the constructing model. This is because one of the main issues is that we don't have in 1+3 dimension a model with interaction. But there is another way that was proposed by Hagen-Casteller in the 60s, and to start from first principle. So by the notion of local nets. So we have the space-time, which is typically it's the Minkowski space-time, it could be something else or something. And then for each region on the space-time, we get a phenomenon algebra. And the rules are, of course, the basic principle of the following. We have isotony, so larger algebra gives larger phenomenon algebra. Locality, if two regions are not a space-like separated, means that it's not possible to send a signal from one region, from point in the first region to a point in the second region at a velocity less or equal to the speed of light, then the two algebra should commute. This is Einstein causality, because if two observations are independent, they must commute. And the other is symmetry, Poincare covariance, for example. That's the most natural, but in low dimension, we can have, for example, diffeomorphic invariant, conformal invariant, and so on. And positivity of the energy. So the generator of translation should be a positive spectrum, so positive energy. So in a sense, this association region to phenomenon algebra is a sort of non-commutative chart, because if the algebra was commutative, then we would have just a usual chart. I should be more precisely or precise on this, but let Let's take this just as an indication of what's going on, not a complete statement. And by classical theorem of Risch-Leader, if you take the vacuum vector, this is cycling and separating for all local algebra. It means that if I fix any bounded region with non-empty interior, of course, then if I take any vector of the Hilbert space, can approximate as well as we want by applying an operator localizing this region to the vacuum vector. And so we are in the condition to define the modular operator, the modular group, and the modular Hamiltonian. So what is the meaning of the modular Hamiltonian in quantum field theory? And the first answer came in '75 by Bisognano-Wickman. It was, and it showed that if we take a ringless spacetime, so it's a sort of wedge region, which is shaped this way, all the other directions are free, then the trajectory of the modular group is the trajectory of a uniformly accelerated observer. But modular time is not the natural the parameter for a uniform of evolution for the proper per time, let's say, of the uniformly accelerated observer. There is a rescaling, beta equal 2 pi over a, where a is a proper acceleration. And Sewell commented that this is indeed the Hawking effect. You know that this famous result by Stephen Hawking, that a black hole radiates as a thermal radiation. So from the classical point of view, a black hole should not have any radiation, because gravity keeps everything. But if you regard from the quantum point of view, it emits a thermal, very, very slow, very little tiny thermal radiation, and this is the inverse temperature. And by general relativity, by the equivalence principle, the uniformly accelerated observer is equivalent to gravitation, and then one can get it in this way the Uru effect that was independent, and the Bisognano-Wickman theorem, as observed by Sewell, is an explanation of the Uru effect, and so in a sense also of the Hawking effect. What happened for a bounded region now? In general, the modular group has no geometrical meaning, but something that I did with Hislop long ago. If we are in the conformal case, in the massless case, then it is geometric. It is an evolution that I write here, but it is not important at the moment to understand exactly the evolution. These are the orbit. So in the massless case, the modular group has a geometrical meaning too. Now let me digress a moment about entropy. What is entropy? Of course, entropy, the origin of entropy is thermodynamical by Clausius and so on. But I want to talk today about the information entropy. So suppose we have a finite set of events, x1, xn, and each event, xi, occurs with probability pi. So pi is a number between 1 and 0, and the sum of the pi is 1. And as you know, that the probability of the independent event is multiplicative, but information is additive. So it's natural to consider the logarithm of pi as information, or at least up to a rescaling constant if you want. So Shannon defined this entropy, which is the average information that one has, which is the sum of pi log pi. And then one can also define the relative entropy. So if you have two probability distribution on the same set, then you want to measure how much the two distribution differ, or the second differ, because when you make an experiment, of course, you are always a bit wrong. So, but and the relative entropy is just the evaluation, the mean in the first state, in the first distribution of the difference of the information. In the non-commutative setting, for example, for matrices, if you have a matrix, von Neumann defines the entropy, which is just a state is given by density matrices, and then the entropy is given by this formula von Neumann. And Umegaffi defines the relative entropy, which is exactly, you write what you, for matrices, what you expect from a relative entropy. So this is perfectly good for a finite quantum system. But when we go to infinite system, there is no trace. There is no trace. And then we have two situations. One is there exists a trace, maybe infinite, but it takes continuous values on projection. This is called the type 2 case. This was considered by Siegel long ago in the 40s, but never truly considered after that. And in my work with Edward Witten, that was posted just yesterday, we reconsidered this and showed that this entropy and make a bound of the entropy increase from a subsystem to a system by the, oh, there is an error. I should correct this this slide, that by the logarithm of the Jones index. And this entropy, this bound is optimal in the infinite dimensional case. This is a point which is interesting because there are indications that this situation is interesting in physics, but the most general situation, there is even no continuous trace. And hierarchy, so entropy is not definable, but relative entropy is definable, and the formula was given by hierarchy, by the modular Hamiltonian, the logarithm of the modular operator. The formula is this one. If one compute in the finite dimensional case, this is exactly the Umegaki relative entropy. And the fact that it has all the natural property. It's positive, it's monotonic, and so on. So relative entropy is, in a sense, more fundamental than entropy, in the sense that all entropy quantities can be expressed to relative entropy. So in principle, we could define relative entropy also in type 3 case, but it will be always infinite. So it's meaningless. Now I will tell you how long can I talk again for another. I will talk about standard space. I will tell you. This is a structure, simple structure where you have already modular theory. So you have a complex Hilbert space, and we consider a linear, closed linear, real linear subspace. And then when we have a real linear subspace, we have symplectic complement. So all the vectors, such as the imaginary part of the scalar product, vanish with respect to every vector in the space. And we have a notion of a cyclicity and space cyclic separating. This is the most general situation is when the space is cyclic separating. And then one can define this Tomita operator, if you want, though it was not defined by Tomita. That's one that goes from psi plus IH to psi minus H. This is an operator, it's an involution. The square is identity, and the adjoint of the Tomita operator is the Tomita operator of the symplectic complement. And take the polar decomposition, and then we have this theorem that the logarithm, the modular Hamiltonian, the exponentiated with one parameter unitary group that leaves this space invariant, and the modular conjugation maps the standard space in the symplectic complement. It was implicit in some work, implicit, also explicit, but not emphasized already in the 70s in a couple of papers. And this is important. Okay, in several contexts, I will skip this, but it is important because it allows to go to define modular theory beyond phenomena, just with a simple structure, Hilbert space and real linear subspace. And if in the factorial case, which means that the symplectic complement has no point, no vector in common with the space H except 0, one can define, of course, the projection, symplectic projection, cutting projection, and some miracle, this cutting projection is expressed by the modular data. It is not important that you understand this formula right now. It is important that you understand that this cutting projection is expressed in terms of J and delta. So the general picture is the following. We have, once we have Hilbert space, we have a real linear subspace. Then we have they form a certain subspace geometry. If you complexify then internal and then we have so the complex structure play a role, and then we have the modular data. These three things are equivalent, but we can go with the cutting projection out of this picture. We can be specific in quantum field theory because the cutting projection will be always geometric in this picture. So this is what will be the way to define, because the cutting projection will be just to cut the Cauchy data of the wave. You have a region, a wave is expressed by Cauchy data, and then you put the Cauchy data 0 out of the region. This is the cutting projection, which is of course a geometric operation. And then we can define an entropy, and the notion of the entropy of a vector in a complex Hilbert space with respect to a closed real linear subspace. The formula is the following that I have to explain, but if you regard with the real part of the scalar product, it's the expectation value on certain operator, the entropy operator that I define here. So entropy has become an operator. So the entropy of a vector is expectation value. Now, once we have this entropy, we can go back to quantum field theory, and what we do for free theory, when first we make the one particle space. So to every region, we define the space of states of localizing in that region, which is a real linear space. And then there is a procedure called second quantization, which to every real linear subspace give a phenomenon algebra just by while operator. And so we get back to the phenomenon algebra picture, and the entropy in second quantization will be just the entropy of a coherent vector. So the entropy I have defined is nothing else that go to second quantization to consider the vacuum state, and the vacuum state composed with the adjoint action of a while operator, and compute the relative entropy. So there are, as you see, several ways of interpreting this entropy, entropy of vector, relative entropy, and so on. But when we specify Hilbert space as Hilbert space of waves, this will be the entropy of a wave. So this, sorry. So the picture is the following. We have our one particle space, the entropy of a vector. If one particle space is made by wave, we have the entropy of a wave. Then we make entropy, second quantization, the entropy of a Klein cordon quantum field theory. Or we can go from the entropy of a vector directly to the entropy of a coherent state, and then specify this to the free field and get the entropy of a Klein cordon quantum field theory. So the same mathematical quantity can be seen as a classical wave packet, the wave function of a free quantum particle, or a coherent state quantum field theory. So depending on how you interpret, you have three different interpretation of this entropy. And the entropy in the one particle space, it's important to note that the Hilbert space depends on the mass, but the imaginary part of the mass does not depend on the mass, in the sense that on Cauchy data we have always the same symplectic form. This is important because when we go to, for example, to quantum field theory in a Carter spacetime, there is no vacuum vector. There is only class of representation. So the imaginary part is fixed, but not the real part of the scalar product. And then when we compute in a simple model, so let's say, for example, for the Newman current, so this is just the one-dimensional massless case, we can compute this entropy, the entropy on a half line, and then we have, this is the formula, L is a charge, and what comes out is that the second derivative of the entropy is non-negative. And this is quite important because it is related to a very important issue in quantum field theory, which is the quantum null energy condition. So the second derivative, or when we deform a region in the null direction, the second derivative should be non-negative. This is considered as a prerequisite to quantize gravity, because a positive energy energy does not survive, but this quantum null energy condition could survive. And then I, very recently with Gerardo Mozella, I have computed the logarithm, the modular Hamiltonian for a boundary region, let's say a ball in quantum field theory. This gives in order to give the energy density of the wave, and the formula very briefly is the following. As you see, it is on Cauchy data, no? So it is 2x2 matrices. There is something that does not depend on the mass. It is in the massless case, and if we consider the entropy, like entropy, this is an integration with respect to this parabolic distribution. This is the so-called energy density, the energy of density of the wave. Okay, let me go directly to the massive case. What this is a problem that was remain open for half a century, I would say. It was solved in this paper with Mozella, and that what is the modular Hamiltonian in the massive case, and it is a perturbation, if you want, of the massless one, but there is a non-local term, and the surprise was that this local term, there is a local term that is given by this form, it's an integration, this integral, and what was a surprise, this kernel is a Yukawa potential. Yukawa is this potential that was predicted by Yukawa in 1934. Yukawa predicted this Newton, this was the potential that was responsible for Newton proton interaction, and for 2 years nobody cared, but then the particle with this Yukawa potential was found, the pion, and Yukawa was awarded the Nobel Prize. This is the first page of Yukawa paper, and you can read the paper if you want. It explains the story by proposal by Heisenberg, Fermi, and so on, and how he got this idea. But in a sense, he put this potential by ends. Here it just comes from mathematics, from Tomita theory. No? I don't want to say that it is in this way I explained the potential for the pion. I want to say that this quantity is an intrinsic quantity. It comes just from the first principle, and then one can compute the local entropy. Okay, this formula I don't think I have time to enter in the explanation of this formula, but what I want to say, and then when you go for large ball asymptotically, when R is large, let's say when R goes to 0, so the density, then it has an expansion, and this expansion is proportional to the area of the ball, and it's in accord with the holographic area theorem, where the entropy, Wittgenstein, for example, proposed that the entropy of a black hole should be proportional to the area of the horizon of the black hole. And when you go to infinity, then you have a bound which is in agreement with another famous bound, which is the Wittgenstein bound. If you fix the energy, how much entropy can be in a ball or in a boundary region, this is the Wittgenstein bound, and so this also comes from as a corollary of our result in this setting. I think my time is over, so I will stop here.
Thank you very much for your talk, Professor Longo. I would like to ask people, okay, we have already questions. So Giuliano, you raised the hand, go ahead. Giuliano?
Sorry, I was clapping actually, but
okay, so it was not a question, it was clapping. Okay, so
it was maybe, I don't know how much it was possible to transmit, and maybe I have used too many formulas. I don't know.
No. Actually, I could follow, and I think also other people in the group could follow. Farhang, please go ahead.
Yeah. So thank you for the talk. It was very nice and rigorous. I'll have some questions that are kind of general. They might not address the results, but it's about modular theory in general. So one of the things that you mentioned in the introduction about modular group of automorphisms, and that the kind of the interpretation is that they provide an internal evolution in the system. What I don't understand is that they are unitary groups. These are unitary transformations. Yeah.
Okay, the modular automorphisms are automorphisms of the phenomenon algebra, and they are implemented by unitary group. The generator is the log del modular Hamiltonian. So you construct first the unitary evolution on the Hilbert space, but then you prove that this unitary implementation, the adjoint action, gives automorphism of the phenomenon algebra. This, of course, very deep result. In fact, the proof is still quite difficult, but it is a very consolidated result by now.
Yeah, yes, so that's good. But when we think of time evolution in a sense that there is a direction of time, I mean, in physics, naively, we would say that the entropy of the system, let's say von Neumann entropy of the system, should increase as you evolve the system. And that cannot be implemented with a unitary transformation, because unitary transformations always preserve entropy defined in the von Neumann entropy. So usually you restrict these maps and you get some like a channel or some sort of a irreversible transformations, which cannot be implemented with unitary maps. So my question, I guess, is how one
You're perfectly right. But here we are in a modular group described evolution in a thermal equilibrium. So entropy does not change. Of course, it is very important to describe other situations in the way you say. But so, for example, even if we go to the very beginning of my talks, it is not possible to explain the origin of time, because we are already in a thermal equilibrium state, so at least minutes at least after the Big Bang, no? But asymptotically, would say, we are in thermal, so this is a situation. Of course, there are papers and so on with the non-equilibrium, but and for example, I have a paper with Stefan Hollands. We describe non-equilibrium, but in a non-equilibrium thermodynamics. So the situation where we are not in equilibrium. So this is the situation that we have asymptotically, but in a sense we are close to equilibrium. So still physics can be described as thermodynamical, the usual thermodynamical variable. Of course, there are also other works, but I don't think this is a subject of research, I would say. No, so, but of course, important point. That is the one that you mentioned.
Yes, thank you. I would have another question if I can, and that is very speculative. It's about von Neumann algebras, because von Neumann algebras, the way I understand them, they describe quantum field theory or operators on a space where there is no gravity in some sense. We can go small and small and small as we want. So it's kind of infinite dimensional. The kind of crude question is, do you think if we want to address regimes, Planck regime, let's say, where there is a notion of, but the kind of this picture breaks down, is there some sort of an algebra there from which type 3 von Neumann algebras can emerge as some sort of deformation? Like, is there some approach, or is there some program to describe quantum gravity in a purely algebraic way, let's say?
Okay, if we talk not of quantum gravity, but a combination of gravity and quantum field theory, in the sense quantum field theory on a curved spacetime. So there is no background reaction from the space. Then this is rather well understood so far. No? So what's the structure when we to describe quantum field theory on a curved spacetime? Of course, it's not quantum gravity. Quantum gravity does not exist as a recursive field, so it's difficult to say. But there are, of course, several schools that try to quantize gravity. I don't know whether which will be successful. One thing that has been made is a proposal for quantum spacetime. So where spacetime is made by coordinates, and you declare that these coordinates do not commute. This work by Sergio Doplicher and others, and also the other approach and isodeformation as you want. This exists, but at the moment are really space-time. There is not much about quantum field theory on this. There is some work even on that, but it's not at the level that a theory which is complete or even satisfactory. So just there is much. I think there is other ideas that are needed. So in this direction. And then there is this idea that I mentioned now that to quantize we need also we need to understand for example this positivity of the energy. This idea of the quantum null energy condition is rather recent, and what I can say, for example, there is a very recent work by Edward Witten. It was posted just before Christmas, in which he proposed to consider not the usual phenomenon algebras, but the cross product of the phenomenon algebra by the modular group. This from the mathematical point is well understood, and so to have entropy there with this continuous entropy and so on. But there are, of course, there are, would say, many results, many ideas, but as you know, quantum gravity is still out of reach, so we cannot say which one will be the final idea, if there will be a final idea, because nobody tells us that there will be a theory of quantum gravity. Of course, our experience say yes, but it is a point. Is it true that we are able to describe everything mathematically? Our experience say yes with physics, but it will be like this in the future. Who knows?
Thank you. Thanks.
Are there other questions? No, I have a question. Can you go back, please, to slide number 29? Well, in a sense, is 29. So in a sense, it's related to a part of the questions that Farhang asked with regard to you. So you, in commenting this slide, and you concluded and then passed to the next one, saying that in a sense, for type 3, there is a, I mean, what we obtain is meaningless.
The full notion of the entropy is always infinite, but relative entropy survives. It's a good notion.
Okay, okay, I see. Now it's clarified because you know, just
Yeah.
Okay, excellent, thank you.
So relative entropy, I consider, I'm not the only one, but I consider relative entropy as a fundamental concept concerning entropy. Because even for Neumann entropy, there is a simple formula, you can express for Neumann entropy in terms of relative entropy. So everything, but in centric context, for Neumann entropy is always infinite, so it's meaningless, but relative entropy is still, because in a sense, what happens in quantum field theory typically is that entropy is divergent. And if you have a good approximation, maybe you see how it diverges, there will be some leading terms. So when you compute a relative entropy, you subtract the divergent terms and you remain with some finite quantity. This is the work, for example. This appears in several works, for example, the work of by Cassini and Huerta that I mentioned, and my work with Feng Shu on the Bekenstein bound, just to say something. But this is the idea, to avoid divergent quantities just by subtracting, and then see what remains after subtracting.
Thank you. I also think that it was very interesting what you have shown today to us, and I also thank you for having discussed something that relates to your recent work, especially for philosophers of time. Is important, or at least it became important after, the philosophical discussion in philosophy of physics with regard to approaches to quantum gravity theory. I find very important what you said with regard to the modular theory of time. And let's say I would like to ask you a naive question. So on the ground of what you have shown us today, on the ground of the recent development, do you think that, or how can we define, conceptually speaking, time? Also considering that we are going to work more and more on quantum information, and we are developing quantum computation. So what is, in a sense, the message with regard to temporality that your work wants to convey?
But my message was that time, in this view, time is there is first thermodynamics and then time. Time is a derived quantity from thermodynamics, which is I think I understand that might create some doubts, if you want. Time. So, but if you have a quantum system, and then a state, then it already have thermodynamics. So the interpretation of the KMS condition, which is the equivalent of the generalization of the Gibbs condition, comes for free. So just intrinsically we have evolution. So time, of course, time modulo rescaling, because the parameter can be rescaled, but time comes from non-commutativity and from the thermodynamical interpretation. Of course, other people might think, have a good reason to say that maybe time comes first than thermodynamics, but it's a debate, I think. And there is a paper by Dettel Buchholz recently, where he takes, in a sense, the opposite point of view. He starts with time as a first principle. It's something that we agree without questioning what's the arrow of time, just because we have a past and so on. And then it derives, if you want, quantum mechanics or having a Lagrangian derived, for example, commutation relation. I'm not a physicist, although I work with physicists and I'm very interested in conceptual problems. But what I can see as a mathematician, and that this is that there is the message that there is an intrinsic evolution. Only when you fix the set, the algebra observable, and take a state. Then, of course, we can debate over the interpretation. But it is a fact. This is not something. This is something which is so surprising, and so that, of course, one has to meditate on this. It's a very deep result.
Thank you very much. Are there other questions also related to clarification?
Let me say that if you want to ask questions in the future, and if you want to communicate, of course, we can do without any problems.
Well, thank you very much. I really enjoyed the talk, and we'll be in touch for sure. Thank you very much again for accepting our invitation. I think we can thank again our speaker, and
thank you for this invitation. Goodbye then.
Thank you very much, Professor Longo.
Bye.
Bye bye. See you.